Using Cableways as a platform for stream discharge measurements allows measurements to be made at sites that offer the best possible hydraulic characteristics. Bridges are often placed at sites of natural constrictions or designed to constrict flow so that the bridge can be made as short as possible. Constrictions can force changes in flow direction, velocity, and flow regime. Also, bridges are often not placed normal to flow, making it necessary to apply correction factors to measurements. A cableway eliminates the need to expose employees to traffic hazards. Finally, many cableways have been built at remote sites where bridges are not available. These cableways offer the only means of making high-flow current meter discharge measurements at such sites. The video that follows shows the uniform reach near the cableway on the Swan River near Big Fork, Montana. The cable provides a track for a car from which hydrographers can make a current meter discharge measurement. The car is released from one end of the cable and because of the sag in the cable, traverses part way to the other side. The car should slow as it proceeds uphill to the A-frame or anchor on the other side. The video that follows shows what a ride on a cable car is like.
Okay, we're about to start our measurement here on the Middle Fork of the Flathead River. Discharge today is going to be around 9,000 CFS. Got a channel width of about 300 feet. I'm going to go ahead now and release the car, and we'll begin at the left edge of the water.
Two types of cable cars are in general use. Both cars have room for two persons. Stand-up cars are often more practical when spans are long and heavier sounding weights are used. Although some cable cars are moved using electric or gasoline motors, most are pulled along the cable using one of several styles of pullers. Pullers must be sized to match the diameter of the cable so they don't slip and can be removed easily from the cable.
This is standard cable puller. It's on the cable. If I want to go toward the right bank, pull it off, put it back on this way, and I can pull in toward the right bank. Coming toward the left bank, I pull it off, put it on this way, and I can go toward the left bank.
As mentioned on the last slide, a braking system is required to stop and hold the car on station. The relatively new sandpoint brake, which is an effective way to slow and stop the car, is shown here. Also shown here is a car puller with a leather strap attached. The car can be allowed to slowly roll over this leather strap to stop and hold the car. The video that follows shows a third type of brake attached to a sit-down cable car. Where none of these systems are available, a rope blocked between a sheave and the cable can be used as a brake. Cable width is measured using marks on the cable. Cables are usually marked in 5 or 10 foot intervals with double marks every 50 feet and triple marks every 100 feet. When looking downstream, cables are usually marked starting at the left end of the cableway. You must keep track of the markings as you move across the cable. Marks should be regularly checked by stringing a taut tag line above the cable. Too much sag in the tag line may give incorrect distances between cable markings. The video that follows shows how cable markings are used to determine stationing along a cable.
Okay, we're going to move to our next station along the stream. Generally, this cable is marked in 5 foot intervals. We'll use 5 foot for our next station. We move until the sounding cable is directly under the next 5 foot reading. Set our brake, and we're there. Now, if you need to get a reading, a lot of cables are only marked at 10 foot intervals. These holes right here are about 5 feet, so if you need to interpolate between, you can use these holes or this bracket down here if you're coming from the other end. And that's going to give you about 5 feet so that I can interpolate between 10-foot or even 5-foot marks.
Water depth is measured using a sounding cable attached to a reel with a depth indicator. Depth is generally reported to the nearest tenth of a foot. Sounding weights are attached to the sounding cable, so the channel bottom can be sounded and the meter can be lowered into the flow. The weights, which are referred to as Columbus weights, are streamlined to lower resistance to flow. The weights contain a vertical slot at the top and a horizontal hole for attaching a hanger bar using a threaded pin. The two types of commonly used hanger bars and pins used to support sounding weights are shown here. Depth is determined by reading the dial on the sounding reel. Depth is usually set to 0 when cups or rotors on the current meter are centered at the water surface. The video that follows shows this procedure.
Okay, before we take our depth reading, we need to zero the dial on our sounding reel. One way to do that is to center the meter cups at the water surface and set that reading to 0 on the dial, and then begin to lower your weight down slowly until you hit the bottom. Once you hit the bottom, take your depth reading on the dial, add the 1 foot for the distance the meter is above the bottom of the weight, and that'll give you your total depth.
You should sound the bottom carefully to avoid incorrect readings. The weight should be lowered gently onto the bottom and not allowed to scour into the stream bed before you read the depth. The video that follows explains these concepts.
Lower the weight until I hit the bottom. Now at this point, I'm showing 3.6 feet. What I want to take my reading, I want to take it as soon as I feel that bottom. On this stream, it's kind of a luxury. I can kind of test and see where the bottom is because I've got a good hard rocky bottom here. A lot of streams where you've got a soft bottom, especially sand channels, as soon as you hit that bottom, it's going to start to scour out under that weight. And if you hit it too hard or hit it more than once, you're going to get a false reading for your depth. So I get my depth now at 3.6 feet.
A heavy enough weight must be used to ensure that the weight will reach the stream bottom and not be dragged downstream. A rule of thumb is that the weight in pounds should equal the product of the maximum depth in feet times maximum velocity in feet per second. Despite your best efforts to use proper weights, the sounding line is sometimes dragged downstream when it is lowered into the water. This is more likely to happen in deep, swift rivers. When this occurs, you will have to consider applying a wet line and a dry line correction because the length of the line let out from the reel will not equal the true depth of flow. The video that follows shows a weight being dragged slightly downstream. You can see as the weight is lowered, it's dragged downstream just a little bit. A dry line correction is shown in this schematic diagram. It corrects for excess length of line let out from the reel above the water surface. A wet line correction corrects for the excess length of line let out below the water surface. It is a nonlinear function that changes with depth. You cannot apply the wet line correction until the dry line correction has been applied. Both corrections are applied to the nearest tenth of a foot. To apply either a dry line or wet line correction, you must know the angle the cable makes from vertical. This is determined using a protractor mounted on the cable car. The video that follows discusses measuring this angle.
Another thing that we need to watch out for is our drag downstream. We use a protractor on the cable car to set the angle, to read the angle and give us our wet line correction. You can see here we're being drawn downstream to an angle of about 20 degrees. We'd look that up on our wet line correction table, and that will give us a correction for the incorrect depth we're getting by going down at an angle.
You can eliminate the need to apply a dry line correction by placing tags on the sounding line at known distances above the center of the meter cups. The dial on the sounding reel is set when a given tag is centered on the water surface. For example, If a tag is set 2 feet above the meter cups, the dial is set to 2 feet when the tag is centered on the water surface. Tags should be set at distances that will cover the range of depths you expect to experience during the measurement. The video that follows shows tags being used to set depth.
Another way to set your depths, which helps to eliminate your downstream drag airline correction, is to use tags on the sounding line itself. In this case, we're setting the 2-foot tag on the sounding line at the water surface. We then set our dial to 2 feet to read 2 feet. Lower the meter down until we hit the bottom. At that point, we're showing 2.9 feet. We know that our meter is 1 foot from the bottom, so our total depth is going to be 3.9 feet.
A price AA current meter is generally used to measure velocity. The meter is attached to the hanger bar. Which hole is used in the hanger bar depends on the weight being used. The video that follows shows a meter and weight being attached to the sounding cable. Lucky Soltz does not have on a PFD when he retrieves the cable. This is because water on this edge of the stream is only several inches deep. In general, you should have a PFD on when working around a stream. Velocity is determined by counting current meter revolutions and using standard rating tables, just as is done when making weighting measurements. A price AA meter usually is used from Cableways. The video that follows shows Lucky Soltz measuring velocity from a sit-down car across the Swan River near Big Fork, Montana.
Yeah, I got a reading of 64 clicks in 41 seconds.
WRD Memo 91.42 mandates that all cableways be inspected by a trained inspector every year, and the results of those inspections be sent to the regional hydrologist. WRD Memo 91.42 states that you must perform a visual inspection of the cableway prior to use. While working on cableways, it is often tempting to grab the cable for support. You must resist this temptation at all times. The video that follows emphasizes this point. Although many job hazard analyses require the use of gloves while working on cableways, this should not be used as justification for grabbing the cable.
One thing you really want to watch out for when you're moving around on the cable, it's really easy to do. Grab hold of the cable and then step on the car, or do something when the car may not be secured. It's real easy for that car to start moving and come right over your hand. In this case, we've got a shield on here, but this shield will take off a lot of skin when it hits your fingers. Always, when you're moving around on a cable car, make sure that you have hold of the car itself. That way, if it moves, at least you're not going to lose a finger or something. So try to keep your hands off of the cable at all times.
WRD Memo 99.01 requires use of breakaway devices that will allow the cable to break free of the reel and cable car should the meter and weight assembly snag debris. The breakaway device is shown on the photo on this slide and discussed on the video that follows. A reels not retrofitted with a drag brake and APAC reels are exempt from this requirement.
Okay, one thing you always need to watch out for anytime you're making a cableway measurement, but especially in the spring during high water or high flows when the flows are coming up, you always want to watch out for debris in the water coming toward you. And the thing that'll get you will be the submerged debris. A lot of times there'll be debris that's just under the water that you won't see. So you need to bring your meter up every once in a while and check and look for small debris that might be affecting your meter. If you should happen to catch a big piece of debris and it starts pulling your meter downstream, first thing you want to do is try to release your brake and let that cable out. And you should have at all times a breakaway device on the end of your cable, so when it hits the end, the debris can take the meter and not you downstream. The other thing you can do, you should always carry with you a pair of side cutters or cutters of some sort that you can cut that cable if you need to. If you can't release the brake, if you have another problem, if you need to release that weight before the cable pulls you too far downstream, you can use your cutters to do that.
To Two types of sounding reels commonly used in WRD are shown here. Power units are available for both reels to assist in raising and lowering larger weights. Sounding reels are equipped with depth indicators. The video that follows shows the depth indicator dial and discusses how it is read.
The sounding reel is set such that your 0 point is this little logo right here. Anytime that your 0 is showing in the little top window, once you've set your reel, then as long as that 0 is showing, you're between 1 and 10 feet. When the 1 shows up, then you're between 10 feet and 20 feet, same way all the way down. Once the 1 is gone, the 2 foot will show up and you'll be in the 20 to 30 foot range.
Most indicators contain a spiral dial, which can be used to determine the location of 8/10 the depth. For example, on the photo shown here, the small number 1 on the spiral dial is located at 8/10 of a foot. If the depth was 1 foot, setting the meter to 8/10 of a foot, the location of the small number 1 on the spiral dial, would be 8/10 the depth. The video that follows shows how the dial is set and how the spiral dial can be used to compute 8/10 the depth.
Alright, we've lowered our meter down until the meter cups are now at the water surface. We'll zero our dial and lower the weight until we hit the bottom. As we get close to the bottom, we want to slow down so that we hit the bottom gently so that we get a good depth reading. The depth is now reading 4 feet. We add the 1 foot that our meter cups are above the bottom of the weight. Gives us a 5 foot total depth. We need to be 2/10 off of the bottom for our 8/10 reading. So we'll now come up 1 foot, but since our meter is already up 1 foot, we don't need to move. We're now going to take our 2/10 from the bottom, 8/10 from the surface reading. You'll notice the spiral dial is now reading 5 feet, which is our total depth. At that point, we'll go ahead and take our 8/10 velocity reading. Okay, now we need to bring the meter up to the 2/10 depth. 2/10 from the water surface is 1 foot. Since our meter cups are set at the water surface, we come down from the water surface 1 foot to take our 2/10 velocity reading.
Velocity meters and weights are attached to the sounding cable using hanger bars. The two types of bars commonly used by the USGS are shown here. The multiple holes in a smaller bar properly position the meter above the weight. This slide shows how the velocity meter should be attached to the hanger bar given the sounding weight being used. The heavy hanger bar shown here is only used when 200 and 300 pound weights are used. You must know how far the meter is above the bottom of the weight. The table on this slide shows the distance the meter will be above the bottom of the weight when various weights are used. Only configurations shown here should be used. You must know how far the meter is above the bottom of the weight because you zero the depth indicator on the sounding reel when the meter cups are at the water surface, or you use tags to set the depth indicator. This means that the depth indicator shows the depth of the current meter below the water surface. You must therefore add the distance between the meter and the bottom of the weight to the depth shown on the depth indicator to obtain the total depth. The video that follows, which was shown earlier, shows how total depth is determined.
Okay, before we take our depth reading, we need to zero the dial on our sounding reel. One way to do that is to center the meter cups at the water surface and set that reading to 0 on the dial, and then begin to lower your weight down slowly until you hit the bottom. Once you hit the bottom, take your depth reading on the dial, add the 1 foot for the distance the meter is above the bottom of the weight, and that'll give you your total depth.
The photo on this slide shows how a meter should be suspended when using a 30-pound weight. The photo on this slide shows one of two ways a meter can be suspended when a 50-pound weight is used. The photo on this slide shows how a meter should be suspended when a 75-pound weight is used. With this arrangement, the meter is 1 foot above the bottom of the weight. The table on this slide shows the minimum depths where velocity can be measured with confidence using various suspension configurations. Suspensions are designated by the weight size and the distance between the bottom of the weight and the meter. The remainder of the class will be used to show how concepts presented in the previous parts of the class were used to make a discharge measurement on the Middle Fork of the Flathead River in Montana. A pre-use inspection was performed before the measurement was made. The next few slides summarize the pre-use inspection. First, the A-frame was briefly inspected. Condition of the A-frame is summarized in the text and photos on this slide. Then the platform was inspected. Once again, the photo and text on this slide summarize condition of the platform. The cable was found to be in good shape, except that branches had grown over the cable. These branches were removed so they would not strike the car and its occupants as the car was released. There was an adequate number of cable clips on the main cable, and they were installed correctly. Although slightly buried, the anchor was found to be in good shape. Text on the slide contains additional information about the anchor. Prior to the measurement, you should always do a pre-use inspection. This is the anchor block on the left bank, showing that the concrete is exposed. The U-bar has a little bit of dirt around it, but it's basically in very good shape. Turnbuckle is tight and in good shape. There are adequate number of clips on both the back stay and the main cable, and they're installed correctly. Cable goes over the saddle block correctly. Saddle block looks like it's in pretty good shape. This Cableway has a extra cable for marker balls. It's strung on top of the main cable. The stand-up metal cable car is in good shape. Looks like it can bear the load just fine. The A-frame is in good shape. The footing pedestals for the A-frame are contain bolts that bolt the A-frame to the pedestal so that it can't be toppled, particularly if the sounding reel becomes snagged to draw the cable downstream. The steps were installed every time the hydrographer comes to the site, and they're in good shape. The backstays were found to be tight and were not corroded. They were secured using an adequate number of cable clips. This photo shows an upstream view of the site. The video that follows shows the gauge being inspected prior to the measurement.
Hey, we're at the Middle Fork of the Flathead River near West Glacier, Montana. We're going to make a cableway measurement here today. We've made our pre-measurement inspection. Stage right now is about 5.23 feet. Should give us discharge of around 9,000 CFS. We've read the outside gauge and the inside gauge, checked our graphic recorder and our satellite platform, and they're all in agreement. We'll come back after we make the measurement and take the readings again and see if there's any change in the stage during the measurement.
As mentioned earlier in the presentation, we will not spend much time on general concepts related to discharge measurements. Those concepts are discussed in other references like the CD-ROM-based report, Measurement of Stream Discharge by Weighting by Nolan and Shields. We will, however, emphasize here that measurements from cableways must sample the cross-section just as completely as measurements made by weighting. This slide summarizes general criteria for both types of measurements. The video that follows shows the start of the measurement.
Okay, we're at the left edge of the water now. We're going to determine the left edge of the water from the cable markings. Cable's marked every 5 feet. If we count from, we can see a 50 mark. If we count from there to about 65, our weight is almost at the edge of the water, so we're going to call the edge of the water 65 feet.
The top part of the front of the measurement note sheet is shown here. From this you can see that the stage varied little during the measurement and that a discharge of 8,760 cubic feet per second was measured. The inside gauge at this stilling well site was read before and after the measurement. Gauge heights that occurred during the measurement were read from the graphic recorder after the measurement. Part of the inside of the measurement note sheet and the cross-section that was measured are shown here. The The left side of the channel was relatively shallow. Velocity was measured only at 6/10 the depth on this side of the channel. The video that follows shows the cable car being positioned to measure depth and velocity at the first measurable subsection.
We're going to move out to our first station here. Now this particular site, we've got real shallow water. We're not going to get a good reading. We'll just get kind of an attempt at an estimate of what the velocity is and the depth in here. I think we can measure it from the meter cups, the percent of the meter cups. Okay, we mark down the left edge of water. Our start time is 13:40. Our start distance was 65 feet at the left edge of the water. Depth was 0. We're now at 72 feet. And depth of 1.5 feet. We had a velocity 26 and 41.
Depths and velocities to be expected during the measurement were estimated by reviewing previous measurements made at similar stages. Based upon this information, a 75-pound weight was used for the measurement. Actual data from the measurement showed that the maximum depth was 7 feet and that the maximum velocity was 8.5 feet per second. Using the rule of thumb presented earlier, the 75-pound weight chosen for the measurement should have been adequate because the product of the maximum depth and velocity is 59.5. Despite using a 75-pound weight, the meter assembly was still dragged slightly downstream. You can see this in the video that follows. Using tags prevented the need to apply a dry line correction. The angle was not felt to be severe enough to warrant applying a wet line correction. Subsections in the middle and on the right side of the channel were deep enough to require measuring velocity at 2/10 and 8/10 the depth. The video that follows discusses one of those subsections.
Okay, I'm now at 140 feet. I'm going to set my 2-foot tag, set 2 feet on my dial, lower it down. This side I passed 5 feet. I want to check my 5-foot tag and make sure that I don't have too much downstream drag. It looks like 5 feet checks on here, so I go ahead and lower it down.
The measurement was completed when the right edge of the water was reached. The video that follows shows the right edge of the water and summarizes the measurement.
Okay, we've reached the right edge of the water now. Looks like it's going to be at about 335 feet, so we'll mark that down. Mark down that we're at the right edge of water. And the time, which is 15:20. We've come about 230 feet and doing 2s and 8s most of the way, mostly with 10-foot sections. The velocities and depths and everything were pretty even, so we're going to call it a good measurement. We're going to finish up now and head back to the left bank and put the cable car away.
The gauge was visited after the measurement was completed. During this visit, all gauges were read, the measurement was computed, and plotted on the stage discharge relation for the site. The measurement plotted within 3% of the rating, therefore a check measurement was not needed.
Okay, we're back at the gauge house now after completing our discharge measurement at the cableway about 1/3 of a mile downstream. We've made our final inspection, noted the gauge heights and the gauge height change while we were measuring, computed our measurement and entered it in the gauge house log. and we're done for the day.